Our next session is hosted by Dr. Garrett Grolemund. He's working at RStudio. And it's especially for us as Tech Academy a great pleasure to have him here today. Because as some of you might know, our student initiative is hosting a program for students who can learn programming in R. So all of our students that have done their R programming courses with us already know Garrett from his online courses and also from his book, R for Data Science, that he wrote together with Hadley Wiki. So as the principal data science educator at RStudio, he's not only a great art teacher, but also one of the most proponent advocates of a more reproducible approach to science. And that's what his talk is going to be about today. So he will show us how code-based technology can solve one of the biggest messes in science, the reproducibility crisis. So please join me in welcoming Garrett Grolemund. The stage is yours.
Thank you, Lucas. Let me start by sharing my screen. Get this out of the way. So it's not. And then, Lucas, is it possible to tell me if you're seeing my slides in a reasonable manner?
We're seeing everything.
Okay. I'm very happy to be here from so far away in the United States today because I want to talk about a story. It's a very important story. It's one that's still playing out. The ending hasn't been written yet, but it's one I'm peripherally involved with. And it's the story of how data has almost undermined science completely, but how data also, at the end of the day, is saving science from the crisis it created. And what I'm going to talk about is this crisis. We're going to start in the middle of this story. What is happening? What's going on? How did data cause this to happen? How is data solving this? And at the very end of the talk, we'll talk about what this means for the future, because there's some big implications for what's going to happen now that I think are pretty exciting, but not everyone has thought through yet. And all of the ramifications still need to be explored. So let's start with the replication crisis. Come back with me to the year 2012. The Amgen pharmaceutical company, the screen's black, that's okay if you're wondering. The Amgen pharmaceutical company does research in-house to take academic studies, research studies, and evaluate them to see if they might be the basis of some sort of drug that Amgen can manufacture and bring to the market. And normally when Amgen does this, they keep the results of their replication studies in-house because it's a competitive advantage. But in 2012, Amgen started to notice a pattern that was so alarming, they decided to go public with it and share what they're finding with the world. And what Amgen noticed is they had replicated or reproduced 53 landmark studies. Now, landmark is Amgen's word, but that means these studies are influential studies that other studies relied on. So Amgen thought they'd recreate them and see what they could learn from the study. And what Amgen noticed is out of those 53 studies, they could only replicate the results of those studies. Now, by replicate, what I mean is first they could reproduce the study, and the results that they get when they did the study over would be the same results that were reported. So in all but 6 of these studies, they either got different results or they couldn't even complete the study the way it was described. Now that's pretty alarming news because these were influential studies that had been accepted by the academic community. And after Amgen made this announcement, Bayer Pharmaceutical Company came out and said that they see the same thing. They could only replicate about 25% of the results of the studies that they study in-house. Since then, this has been studied in depth, and our best estimate is that 75 to 90% of preclinical results in biomedical research cannot be replicated. From a scientific point of view, that means that the results that have been reported and accepted are very likely coincidence at best and ephemeral, and we shouldn't really base further research on them. But we don't know that, and we do base further research on them, which is incredibly unsettling for the biomedical industry. But since then, people have looked at other areas of science, and science seems to suggest that this replication crisis, this inability to replicate results that we thought were tried and true, applies to many different areas of science. For example, a study of 100 important psychology studies found that only 36 of them had results that could be replicated. A study of 59 very important economic studies found that only 29 of those had results that could be replicated. And then finally, a study of 21 articles from the journals Nature and Science, which are the premier scientific journals, at least in the English-speaking world, found that only 13 of those 21 studies had results that could be replicated. Now, that's not half bad, but it almost is. And I'm not making these up. I mean, here's the citations for those studies of replicability within the different fields. But this is a big deal because these scientific fields are humankind's best hope for doing things like healing the environment, curing cancer, creating wealth. And they cannot do those things because almost half of their results appear to be untrue. And no one really knows which half until we go back and reproduce those studies. Now, this is a fascinating research to me, and I wanted to contribute to it in my own special way. So I did a study myself to help put this in perspective. I took a coin and I flipped it 21 times. And I counted up how many times the coin came up heads. And that was 12. And that result looked a lot like the Nature and Science result. And you might be suspicious at this point in my talk, but I assure you my results are more or less replicable. But what they unfortunately insinuate is that if you take any given scientific article and want to know whether the results are true or replicable, it's a random toss-up whether or not that will be the case. And the public quickly caught on to this. You'd see headlines in newspapers like, this is the New York Times, why do so many studies fail to replicate? Psychology's replication crisis, it's running out of excuses, The Atlantic. Or the breakdown in biomedical research, the Wall Street Journal. And there have been more headlines, and there'll continue to be more headlines. So what not only is this not good for the progress of scientific research, but it's kind of becoming a credibility crisis for anyone who works with science. So that's the crisis. Now let's look at how it came about, because interestingly, data is one of the culprits. If you look back at the history of science, sort of gloss over it, modern science began as groups of intellectuals began to write letters to each other, talking about the experiments they were doing and the knowledge that they were collecting. In 1660, this was sort of formalized in London with the Royal Society of Science, and people would actually formally get together to share results, debate their implications or their value, and so on. And this model of science led to the discoveries that you might call the golden age of science, or the classical age of science, like Newtonian mechanics, discovery of vaccinations, thermodynamics, then electrical dynamics, germ theory, and even relativity through Einstein. And all of these discoveries were made essentially through two things, experimentation and observation. Many of these things involved math, but they were actually discovering that mathematical formulas describe the world, and they proved that by observing the world. For example, Einsteinian relativity, one of the ways that we conclude that was true is it made a prediction about the orbit of Mercury, that it would have some sort of wobble. I don't understand it in detail, but other theories wouldn't predict this wobble. And then we went and observed the orbit of Mercury, and it was actually there. And that was a sign that the mathematical formulas of special relativity actually describe the world, and therefore we could use them to do other things. This is a tremendously remarkable period. And then in 1925, Ronald Fisher in England popularized p-values. Ronald Fisher was a mathematician and a geneticist who had been assigned to an agricultural station in England that had been collecting lots and lots of data of how different fertilizers affected different crop yields and similar related things. And it is sort of the culmination of a trend that had been going on. As science progressed, our ability to measure things and our realization that it's important to measure things grew and grew. And as a result, data started to grow and grow as well. And so when Ronald Fisher got to the agricultural station, there's plenty of data there waiting for him. And he devised some mathematical tests that allowed him to make inferences based on the data. His classic book is Statistical Methods for Research Workers. And in that book, he popularized the idea of p-values. And a p-value is a really elegant mathematical way to deal with the problem of sample variation, or sampling itself. If you want to learn about an entire population that you can't possibly observe, you could look at just a portion of it, a sample of that population, And your estimates will be pretty good, but they will be off by a little bit, and p-values allow you to quantify the uncertainty involved in this process. Well, like I said, I think that is an elegant mathematical solution to a particular problem, but the statistical community is pretty certain that p-values are the source of the replication crisis. In fact, the American Statistical Association in March 2019 published an article that said, please stop talking about statistical significance, and statistical significance is only something, it's only a way to describe when you have a result with a p-value below a certain threshold like 0.05. And up until now, that was sort of the bread and butter of statistics. So for the American Statistical Association to say to stop using this technology would be sort of like the American Tobacco Association saying, please stop smoking. Why would they do that? It's a real reverse space. Well, p-values do have some known problems. The first problem is they're fairly misused. Nature, again, the journal did a study of how other studies were reporting p-values. They looked at 791 articles, and they found that over half of them, slightly over half, 51%, were interpreting their own p-values incorrectly. So that's not good. People don't really understand what they're doing with their p-values, but p-values have other problems. A p-value, the way we commonly use it, means that your finding has a less than 1 in 20% chance of being a coincidence or randomness. And this creates a file drawer problem because 20 teams could study the same problem, and one of them, through random chance or coincidence, could find a relationship that doesn't really exist. The other 19 would not find it. The other 19 would not publish, but that one group would publish. And so the published literature would make it seem like this is a real thing, where in reality, it's not a real thing. And this alone could be the source of our replication crisis. Alternatively, you could do one study that tests 20 different hypotheses, and one of them by random chance would be significant, and you just publish that one, don't mention the others. It's a problem that p-values don't prevent. But there's a larger problem with p-values, and this is the real root of the replication crisis. This uncertainty created by sampling from a population is an important source of uncertainty. But if you're learning about the world with data, it's only one source of uncertainty in the entire process. And as a culture, we've come to regard this p-value, which talks about this one arrow in the path here. Every bullet point here, by the way, is another source of uncertainty. Culturally, we've come to accept p-values as an estimate for the uncertainty in the entire process. And they were never designed to do that, and there's no way they could do that. But we use p-values as if they justify all of the research that we've done. And if we have the right p-value, we can assume that everything turned out correctly. That's certainly not the case. And why do we behave that way? Well, I think if we go back to Ronald Fisher's book, the one I cited earlier, we could identify pretty quickly. Here's a page, almost at random from the book. It's page 100. You look at the page, what do you see there? You see variables, factorials, addition symbols, exponents. It looks like math. And that is a problem. All of the numbers, all of the data we collect allow us to start applying math to those numbers, extend them further and draw inferences. But let's do a thought experiment, see why this would be a problem. Here's two groups of words: discover, hypothesis, best guess, messy. Another group, prove, axiom, certain, logical. And if I ask you which words you associate with math, it would probably be the second group: proof, axiom, certainty, logic. This is what math is. But if I asked you to associate one of those groups with science, it'd probably be the first group. Science is a very messy process of experimenting and observing and getting your hands dirty. And no matter what you observe or what you hypothesize, there's always the chance that new data can come in that would suggest that your hypothesis is wrong. At the end of the day, there's very little certainty, although we could certainly get close to certainty in some cases. But science is not math. And p-values made us think that we could make science math and we could prove that things were correct. So this is how data got us into the problem. As data and numerical measurements increased, we began using more and more math in our methods. And somewhere along the lines, we started to assume that we could generate these numbers that were essentially mathematical proofs. And we could use those to justify publishing some studies, not publishing other studies. And then we assumed that the studies that got published were true. Well, unfortunately, that's not the case. But data is also getting us out of this difficulty. All right, so here's the main point up to this point in the story. We confuse science with math and act as if we could prove our own findings, our scientific findings. And some of you might say, well, Garrett, you can prove it. That's called hypothesis testing. But hypothesis testing does that not actually prove your findings. If there is a probability model involved with your findings, then there is some probability, non-zero probability, that your findings could always be false. It's just we round that probability down to 0 if it's less than 1 in 20. And that's the point. All right. So how did data solve this crisis, or how is it solving this crisis? Well, we continued to collect data. And at some point we couldn't really, use just plain math to analyze the data. So we started using computers, and we started using computer code to analyze that data. And this has shifted things back in the right direction. Let me give you an example of what code can do for us, and then I'll tie it back to science and data. My example is open source software. If you use the R language or Python, you're probably familiar with open source software. It's software developed in the open. Anyone can access its source and add to it or change it to make it better. And one of the most popular places for doing open source software is a website called GitHub. GitHub works a little like this, which illustrates the whole concept. If there's someone like Hadley Wickham and you make some software, that's what the book is here. Anyone on GitHub could copy that software. I could copy what he wrote in its entirety, in its original form, and I'll have a version of all that code. And then I could start tinkering with it. I could change in some ways that might not be that great, but maybe some ways are really good. And so I improve it. And now I have a project that's a little more advanced than Hadley's project, but in the open source software world, it's very easy for Hadley to accept my improvements into his project. Now his project is advanced. And in this way, hundreds of contributors could be working with Hadley, and everything that they find that's an improvement, he could add into the project, carrying the whole thing forward for everybody. And all the things that are dead ends, well, they just don't get added to the project, and that's fine. And in the open source world, you might have multiple projects trying to solve the same problem. And through this sort of process of collaboration and improvement, some projects will take off and get better, and they'll draw the interest of more collaborators, and those collaborators will help improve those. And eventually, after a while, a project might even split into two, and you'll have separate versions that go in different paths. But even though multiple projects started, the ones that aren't that great will be abandoned, and the ones that are good will be further developed until you have a really good piece of software, which is why people use open source software. There are some really good pieces of software coming out of this process. Now, I think this process is very similar to how science was originally. Amateurs, and in a good sense of the word, would push the bounds of knowledge, create experiments, create hypotheses, try to test them. And some of those hypotheses were not good. And like a not good open source project, no one got interested in them, and they sort of just languished and got left behind. But some of them were actually really good and really useful. And people would extend those hypotheses and develop new experiments until our knowledge evolved and became more refined and closer to the truth, or at least more and more useful in the world we live in. So science, what I'm saying is, it's built to follow an open source software process. And that process, you probably know in other ways, it might sound a lot like evolution. And I think it is evolution. I think that it's this mechanism of replication and selection, or heredity and, I don't know, mutation, whatever. But we know that evolution can explain how things get better over time, or how they adapt to their selection pressures over time. And science is a field where the selection pressure is usefulness and truth. We cannot actually prove the usefulness and truth of anything, but we can allow it to evolve towards being more useful and more truthful. P-values aren't necessary for that process. But one thing is necessary for the process. You have to have some sort of source, in the biological world, that's DNA, that can be replicated and tinkered with, mutated, pushed forward, and passed on. In open source software, that source isn't DNA, it's actually code. And now that scientists are starting to use code can serve the same function in science. It could be a source that other scientists can replicate, improve, and share with each other to allow science to evolve. But there is one last hurdle that, until recently, prevented this from naturally happening in science. And that is the ability of code to actually be a source for science. So in the early days of science, when scientists would share their findings, as I was taught in grade school, this was done in reports that followed a familiar pattern. A scientific report would begin with an introduction that explains what hypothesis is being tested, why it's being tested, And then it'd have a very detailed methods section that says, this is how this particular study was done. And that methods section would allow anyone who read the report to replicate the study. Then there'd be a results section that says, what did we discover? And a discussion section that, speculate on the implications of that. And this structure is still seen in reports today, although reports today unfortunately rely much more on what is the p-value for the results and don't always make the methods detailed enough for someone to recreate. And we'll talk about why in a second. But in the earlier ages of science, this report itself would be enough to replicate an experiment. And so for experimental science, this was the DNA, this was the source code, this was what could be shared and extended and improved upon between scientists. And it did work in that way. Well, what happened as we started to rely more and more on data is we would have hypotheses, we would do experiments, but those experiments would return data. And as data became more sophisticated, we couldn't directly draw conclusions from that data. We would have to analyze the data to come up with our conclusions. And this changes the process in some ways, some important ways. IMRAD, which is an acronym for that, Introduction, Methods, Results, and Discussion, it's pretty good at covering this process if the conclusions follow directly from the data. But what if you need to visualize your data or transform it or even model it to draw a conclusion? IMRAD wasn't so good at explaining the assumptions and the techniques that you're using there. And actually, if your data is pretty large, you're going to need to use a computer to visualize, transform, and model it, which means you're going to have to import that data into the computer. You're going to have to save that data somewhere because it's probably fairly large. You're going to have to tidy that data. Every piece of software expects data to come in a certain format, so you have to get that data into that format. And it's a process that's not trivial, but it's also not one that you can describe in detail in a written report like IMRAD, which broke the process down. How do you create some replicable source that you could share with others when that source has to, when you're using code, you're using data that has to be shared. There's reasoning guiding your process that's really tied to the code and the data. None of that really fits in the traditional scientific report, and people haven't put it in the scientific report, but they figured including the p-value would be enough. All right, so how do we create a DNA, a open source that covers all of this and let science evolve again? Well, R Markdown is something that does just that. R Markdown is a piece of open source software itself. It's one that I evangelize. I teach people how to use it. I don't think I could claim to have added anything to it, but I did make the website for it. But let me show you what R Markdown is, because it's pretty novel. This right here, what you see is an RStudio IDE. It's just a place to write R code or scripts that are written with the programming language R. And what I have in the window here is a document, an R Markdown document. It's written in the R Markdown format. And it contains these gray sections. These are code chunks. And what you see in here is R code. So if you've never seen the R language, this is a bit what it looks like. And what this is doing is it's loading some software packages. One of them contains a data set. And then it's doing different things to the data set and saving different variables. That's the sort of thing that a scientist might use to analyze data. But in between these gray code chunks, an R Markdown file also has white fields of just plain text. I have put a lot of stuff into my plain text here. This is more R code I'm calling within my text. But an R Markdown file is a very simple idea. It's a plain text file that allows you to combine executable code. It could be written in R, or despite the name R Markdown, it could be written in Python or SQL or any other language. It allows you to combine that executable code in with regular narration, written in English, German, whatever human language you want. It's a simple plain text file. These are just characters, you call it txt if you want, but I call it R Markdown. And if you use an R Markdown file in a piece of software that's aware of what R Markdown is, then you could use this file to generate a human-friendly report. So I'm going to click the submit button. I clicked. And it uses the code over here that I made to make this report here. This example is almost trivial, but the principle is quite profound. You could create a 20-page report that fits all sorts of models and shows the results. My report here contains the text in my document. Some parts of the text I've written with code. So like these numbers just come from looking up the objects I made up here with R. And then the graph is made with code here. And the code doesn't have to show up in my report. I set it up so it won't. Just the products of the code show up. So I could pass this on to a boss and he could see the report. But I could pass the R Markdown itself on to another scientist. And as long as the code here accesses the data, so they could access the data with the code, then this is a reproducible record of my work, my scientific work. And they could extend this or share it and so on. And the R Markdown document becomes what the original scientific document was, or what code itself is for open source software. It becomes a replicable source that allows evolution to occur in this field. So that idea is spreading, this idea of computational documents. And that idea is going to save science from the replication crisis. It'll look like, it'll look like that. Now that we have so much data that we've had to rely on code, we're starting to solve multiple problems with code. And one of those problems is the ability to replicate and select good scientific research. And by reinstating that ability, science is going to evolve towards more and more refined results in the same way that it always has, except for this brief hiatus where we use p-values to treat our scientific work as if it was mathematics, because the numerical side becomes so complex we could not pass on our work in a replicable way. So that's the end of the crisis, or it will be as that starts to spread, but it actually has a very profound meaning for the future. And that's what I'm going to spend the last few minutes showing you, because this is what gets me really excited at the end of the day. Here's this report I made with this code over here. And now that I've made this report, I could share it online, which I have. Let's see, this is still fresh. I have to refresh it. So this is shared on a server that RStudio, my company, hosts. It's called RStudio Connect, but it's the same report here. What's interesting about this is this server knows that it's sharing reports that have code attached to them. And it knows that it can execute that code to reproduce the report. And if you set that code up in the right way, for example, imagine you set this code up such that it always starts by pinging a database and pulling in the most current version of the data. Then you could set this report up on the server and do things like schedule it. You could say, hey, let's refresh this report every day or every week on a Monday, so it always shows the newest data. And I, as a single scientist, could set this all up, and then it'll run in perpetuity as if there were a team of data scientists supporting this report. And the CEO of my company could always come look at it and benefit from the most up-to-date thing, but I don't have to do any more work after I wrote that report. And more importantly, the CEO or whoever the consumer is, they don't need to know anything about the code because I did that once and took care of it all. And now the servers go execute that code in the background because it knows what's happening. By the way, this report here, I had a child recently and I was looking up, name popularities, trying to decide what to name them. So I made this little report that I could type in a name and it would show me like the history of how popular it was. And that's another thing I could do with my report. So I don't actually want to schedule this. But since the code is there, and since I arranged it to take an input of a name, this server knows that the code can take an input. And right now the input's Garrett, but if I wanted to look up a different name, say Michael's unpopular, I could type in the input there. The server's going to take that and just rerun the code that's behind this report, but using Michael as the input. And this is a free account, so it's not very fast or anything, but now I get a new report. All the language is the same, but every code product in the report is now using a new input. And since the code writes some of the language, like the title and the number of children, this is now updated to my input, Michael. And I could put this on a website and open up to the world, and people could use it to explore every single name. There's already websites that do that, so there's no point. But this really increases the leverage I had from writing that one single report one time with one bit of code. Like all I had to do is write this. And now think of the things people can do with it. And this is just a trivial report. The principle is actually quite profound. In fact, I think there's a historical antecedent for that, and that would be the printing press. When Steve Gutenberg, that's a bad American actor. When Johann Gutenberg brought the printing press to Europe, because it did pre-exist in China, and popularized it, it allowed people to reproduce the written word very quickly. And the written word contained knowledge. So it allowed knowledge to be built up and stored and shared in ways that were never possible before. You could recreate books, monks were doing it, just not at scale and not in a way that was almost automatic. But once the printing press made reproducing the written word automatic, it created new industries, like the printing industry that's still with us today. It created new cultures. People could, for example, read the Bible, and we know that that had some profound effects, not all of them positive. There were wars. But it created new opportunities in a way that before the printing press really came about, no one quite understood. Now, I don't think that putting code in documents and making them executable is going to change the world to the same extent that the printing press did, but it could. People make products that host documents with executable code in it and are designed to allow users to benefit from executing that code without having to be programmers. That opens up new worlds of opportunity. I'm convinced it's going to open up new industries, and it's going to change the way we do things in ways that we don't yet appreciate. And that's going to be the lasting impact of the replication crisis. So let's stop there. It's the end of my talk, and it also saves us about 10 minutes for questions.
All right. Thank you so much for this amazing talk, Garrett. I was especially struck by how big the mess is that science is apparently in there. So in the beginning, when you talked about the quotas, how much research is reproducible at all, that's really just mind-boggling. But let's go first to some questions from the audience. So we had 2 questions from Lazarus and Vera, who were more or less on a similar topic. So Lazo is asking something about the peer review process in science. So usually if you write a manuscript in science, some people who have knowledge in this topic will check your manuscript and assess if it's valid. And he asks, is there something, or should there be something similar as the peer review process when you submit code? And do you feel that this should exist in academia as a standard?
I won't claim to be an expert here, but my opinion is that yes, it should be. I think the peer review process is one of the redeeming elements of scientific literature, even throughout the replication crisis. And even though, once the culture really focused on p-values, so did the peer review process. But still, that was a feature, the peer review process, not a bug. Code can be good and it can be bad. And we've already seen examples where code has failed. Code's not failing because it's not reproducible, but it doesn't always do what we think it does. And I think recently there's a sort of high profile finding where a very popular Python library was either rounding numbers a little incorrectly or using random number generation a little incorrectly, but it actually could affect the results of a study. And if no one was reviewing that code or looking into it, that wouldn't have been discovered. And if people were actively reviewing that code, like through a peer review process, that would have been discovered much sooner and would have caused much less disruption when it was discovered. So yes, we definitely should, in my opinion.
All right, thanks for that answer. So we have another question from Vera, and she's asking, in what ways do the means of data acquisitions, so she means the materiality of an experiment, as well as the social context in which the data is produced, in which way do they add to the described mechanisms leading to the reproducibility crisis?
Well, there's a couple of ways. First of all, to be completely reproducible, you do need to share the data. And that's not always possible, and sometimes for very good reasons. But I think that we can balance out the need for privacy or what have you with the need for scientific research in a way that everyone can be comfortable with. Even the people whose data is being looked at. You can have scientists look at data privately, but that's something that will need to be figured out as we go along. The second thing that we need to think about when we talk about how data is acquired is, if you're making inferences from data, if you're using data to learn about the real world, your results can only be as good as the data, which I guess is obvious. But data suffers from selection bias. Self-selection bias, survival bias. There's all sorts of ways that data can be collected in a way that does not accurately represent the world. beyond pure sampling variation, which p-values get at. My background is in statistics. I have a PhD in statistics, and the field of statistics in a large part tries to account for these things or identify these things. But I'm not sure how aware the larger academic community is of that. Certainly, the more we could educate people about that, the more they can mitigate those things that undermine the quality of data as they do their research. And the more the peer review committees and the people who ultimately, through whatever methods, decide to pursue a line of testing or just abandoning it, like open source software. The more those people are familiar with these things, the quicker we'll be able to iterate on good findings based on good data and identify findings that aren't so good and just leave them behind.
Right. We've got one more question from Lazaros, and he's asking about the pressure that researchers often feel themselves under, and he's asking about, like, if a researcher feels a lot of pressure from the university and for their future career, do you think that this circumstance has contributed largely to the problems that you've described? So he asked if you think that there was a contribution of this pressure to the phenomena of p-value phishing or p-hacking, fraud at all in the reproducibility crisis?
Well, again, I'm not an expert, so I don't want to make accusations, but I'm someone who has lots of opinions. And one of my opinions is that yes, certainly. So what we did is p-values create the rules for a game, and those rules could be gamed. And then the tenure system created pressure that would cause people to want to game the rules or cheat. And then the industry these things are being sponsored by, like, in pharmaceutical research, there's lots of money there. And money is also pressure. If you can produce results, you could get paid quite handsomely. So since p-values do have weaknesses that can be exploited, the pressure creates the incentive to exploit them. I do think that was happening. And I sympathize very much with academic researchers. They have to play the game by the rules of the game. They're doing important work. They've spent large portions of their lives to be able to do that work. But the whole culture is allowing things to slide in a way that we don't like. So they're really stuck between a rock and a hard place. But things are changing. When I was a PhD student in 2012, it wasn't that long ago, that's when I graduated, I worked with my advisor, Hadley Wickham, who creates a lot of our packages today. And we couldn't find funding to support our careers doing what we were doing back then, which was creating the sort of software that allows us to solve these problems. But a year or two ago, he was awarded the top prize by the American Statistical Association for the work he's done. Is so valued now. I don't think he's going to go back to academia, but he surely could if he wanted to. I'm not going to. I haven't been contributing software the way he has, so I'm not even in that position at all. But it's valued now, and it wasn't just 10 years ago. So things are changing, and there should be a bright side for researchers who feel under pressure at the moment with the way things are.
Thank you very much for that answer. So we've got one more question from Dominic, who's asking of your perspective. So he has two options for you. What would be better in your perspective? Upload the code to GitHub of your project and provide the requirement info, or on the other hand, containerize your data and your code, for example, in a Docker, and provide a closed environment.
I don't have a strong opinion on that. If you could containerize it in a Docker environment and make it, so simple for someone to use it to recreate it, that's like 100% replicable. With GitHub, people I think they do need to know a little more to actually set up the computing environment to run your code the way you ran it, which is a problem you're solving by creating a container to do that. Also, GitHub relies on Git. Git does amazing things, but I'm not convinced it does them in an amazing way. There's a huge threshold of learning there before you can use it. And yet, it seems like most of the work is being done with Git. That's where the largest audience is. So even though it's harder for individuals to replicate your work, it's easier to get good selection pressure from multiple people looking at your work using it. So it's a trade-off. I'm not really sure, but I don't think you could go wrong either direction.
All right, so let's come to the last question, and that's more or less a personal question from my side. So many people, what we've seen in our work, they, especially if they don't come from computer science, they fear to start coding at all. So there's this huge threshold that they somehow have to cross to actually start doing stuff with R, with Python or something. And from your perspective as the principal data science educator at RStudio, what would be tips and tricks for people who want to get started in R or in any other programming languages? Where should they start?
Well, I'm going to sound biased, but I believe in what I'm saying. If you are worried about writing computer code, start with R, the R language. R was invented by Bell Labs, the same people who made Unix and C and some really fancy stuff. But at the end of the day, they decided, you know, these programs we made, they're really good for talking to computers, but they're not so great for talking to humans. And what we really need is an interface between C or Unix or Fortran and the human that is human friendly. So the human can write this code, but the code is almost like the way they think anyways, which is very different than how a computer thinks. And so they created S, and S was the forerunner of R. About 20 years later, some professors who were teaching statistics said, you know, we really need a programming language for our students to use, but we can't spend all semester teaching them how to use it because we got to teach them how to use statistics. So let's take S, which is actually really good. We'll round off the rough edges, there aren't many, and make it even more human friendly so the college students can start using it. And the result of that is called R. So R is a language from its DNA that's made to be easy for humans to use. That's not quite true of all programming languages, and it makes a good stepping stone to other programming languages. I tell people, if you could use a calculator like a TI-89 or a fancy graphing calculator, you could use R. It's the same principle. You call a function, you get a result from it, and it just extends that principle to be a whole language. So start there, and there's lots of resources, a very friendly community online. If you want to make it fun and get started, go to Twitter and look for the Tidy Tuesday hashtag. Every Tuesday, this group puts out some data sets you could use, and the Twitter community takes the data sets and makes graphs out of them using R. And then they share their graph and the code that they made, and they give each other tips. And it's a very friendly way and practical way to get started.
All right, thank you so much for those valuable insights, and thank you so much for your time, for joining us here at TechConference. I think we've learned quite a lot from your talk. And yeah, once again, thank you so much on behalf of the team. And this was the TechConference, but it's not completely over. We still have one more thing on the agenda. So please join us now on the stage when we will close the TechConference 2020. And once again, thank you so much for Garrett Grolemund for your time and for this interesting talk. Thanks.
You're very welcome.